Okay, let's begin. So today I'll briefly discuss how you'll go about sizing transistors in your designs in practice. And before that, let me introduce a couple of parameters that we use to characterize transistors, which will also be quite useful when you are doing the design, right? So first, let's say you have an NMOS transistor. What is the intrinsic gain of this? What is the intrinsic gain of this guy? Gm R0, right? And what is R0 in terms of 1 by lambda ID, right? So this basically is Gm by ID times 1 by lambda. Okay. So this guy Gm by ID is a parameter that is quite often used to denote how well a transistor is. And if you think about what this guy is quantifying, it says how much Gm you can squeeze out of a transistor when it's biased with a given current ID, right? So basically, if this parameter is large, which means that you are getting the maximum Gm out of the transistor for a given bias current, right? So in a way, this kind of quantifies the power efficiency of the transistor, right? Basically, if you want to burn, if you want to get a higher Gm, you will have to burn more power. But if the Gm by ID is large, for a given current, you can get a higher Gm, right? So, in short, if you have a large Gm by ID, so this means first you have a large gain that's apparent from here, and it also means you have a good power efficiency. And not just that, so if you look at this ratio Gm by ID, so what is Gm in terms of the current? Yeah, I mean, is there some other expression which relates? It's 2 times ID by the overdrive voltage, right? So this simplifies to basically 2 by overdrive voltage if you follow square law. So if I have a large Gm by ID, what can you say about the overdrive voltage? It's very small, right? So this also says that you have a small overdrive voltage. And what does it mean? Well, you have a current ID, and I'm saying that for that current ID, the overdrive voltage is small. So what does it mean? I have a given current, I'm saying the overdrive voltage is small. So,
first term should be.
What is that first term? WL must be large. Okay. So to get the same current, if you have a small overdrive voltage, the only way possible is to have a large W by L. So it basically says you have large sizes. So if you have large sizes, what can you say about the gate capacitance? That is also higher, right? So you have a higher gate capacitance. I'll call it CG. And if you have a higher gate capacitance, what can you say about the speed of the transistor?
Decreases.
It is small, right? Because large capacitor, you will take more time to charge and discharge. So this means we have a low speed. So basically the point I am getting is this single parameter Gm by ID can tell you all such important and relevant details about the transistor. Okay, and also if I take this ratio Gm by ID, right, I know Gm is proportional to the transistor width, current is also proportional to the transistor width. So Gm is proportional to W, ID is proportional to W. So what can I say about Gm by ID? It is independent of the width. Okay. So is the case with the intrinsic gain, because we just saw intrinsic gain is 1 by lambda times Gm by ID. So this is also independent of the transistor width to first order. So this is the first parameter I want you to understand, Gm by ID. Now, the second parameter I want to introduce is something called transit frequency. Have you guys heard of? Okay, let's see. See, this definition basically stems from the era of BJT. So the definition is this. So let's say you have an NMOS transistor. Say you apply a small signal current I in. It's all biased in saturation, so drain is incrementally short. I know I'll have capacitors from the gate. So this is CGS. I'll also have CGD. Right? And in this case, basically, since the drain is incrementally short, both these guys will come in parallel, right? Good. So in this, if this is the case, can you tell what is V1 of S? V1 is the gate voltage. I'm pumping in a current I in, small signal current. I in of S times?
Upon SC.
Yeah, what is that S times?
CGD plus CGS.
Yeah, CGD plus CGS, so call some total gate cap some CGG. Okay. So this is going to be my gate voltage. So if this current is I out, what is I out of S? Gate voltage is this guy. So what is the incremental current? GM times is gate voltage. So that basically is GM by S CGG. I'll probably write it properly. I'll have S CGS plus CGD times I in of S. Okay, so the transfer function I out by I in is GM by S times the total capacitance you have. So now let us say I take.
You can only say the drain current is GM times.
Yeah, drain current, yes. Okay, I mean, yeah. When I mark this current, I meant the incremental drain current. Okay. So probably I can make it more clear to avoid confusions. Oops. See, this capacitor is basically coming in parallel, right? See? So now it should be fine. This is drain current. Cool. So now if I take the frequency response I out by I in, at what frequency do you think this becomes equal to 1 from this? Yeah, at omega GM by this entire CGS plus CGD, this term becomes equal to 1, and this frequency is called omega t, or the transit frequency, and the Hertz frequency is essentially 1 by 2 pi times this guy. And again, for practical purposes, CGS is much greater than CGD, so we can approximate this as CGS also if you want. Doesn't matter, but I'll just write it completely. So this is the one that will dominate finally. Okay. Now again, this as such doesn't make a lot of sense for a MOSFET. For a BJT it makes a lot of sense, because for a BJT you have a current gain from the base current to the collector current. So this basically defined what was the maximum frequency till which you can get some current gain. But in MOSFET it doesn't make a lot of sense, but still it gives some idea of how fast you can operate the transistor. I mean, if a transistor has particular FT, it doesn't mean you can operate till FT. But I can certainly say that if I have two transistors and one of them has a higher FT, the one with the higher FT can be operated till a much larger frequency. So it still can be used as a metric to compare how fast each transistor is. So, and again, another thing to notice, here again GM is proportional to the width. What can you say about the gate capacitance? It is also directly proportional to the width. So what can you say about FT? That is also independent of width. Again to first order. Cool. So with these parameters introduced, let's start to see how we will go about designing things. So we have looked at how we'll design two-stage Miller OTA. We saw a couple of different ways in which you can go about doing it. And if you remember, the way we finally decided the transistor sizes was, we found the GM of transistors from phase margin omega u and something. We either assume the overdrive voltage or the total gate to source capacitance, and from these two we found the current and W by L, right? And let's say now you are given GM and the overdrive voltage. Let's say this is how we are proceeding. How you will find the current? These two are given. How will I find the current? GM is what in terms of the overdrive? 2 ID by the overdrive voltage. So from this you can find the drain current. And once I know the drain current, I can find the sizes, because this is the equation, right? So if you know mu and Cox, you can go and compute what W by L is. But unfortunately in practice this doesn't work well, simply because this equation to start with is an approximate equation, okay? And in fact this is what we call level 0 modeling for a MOS transistor. I mean, if you want to make it slightly better, you can add this 1 plus lambda VDS and stuff. But still this is a very rudimentary model, and it has what, nu and Cox, lambda and few other parameters. But the actual practical model for a transistor, that will have so many parameters, and in practice we usually have what is called a compact model, and there are a lot of compact modeling people who work and improve the model. And if you take a look at the model file of a modern transistor from a foundry, it will have hundreds and 200s of parameters, and each day this modeling people will keep adding one and more parameter to make the models better. So simply you will have, let's say, 200 parameters for one transistor, and if you are designing a 5 transistor diff amp, you will have, let's say, 1000 parameters in total to deal with. So if you want to sit and analytically solve including all the parameters, it's impossible, right? So we'll see how in practice we do that. And before that, I mean, this equation is not great, but still it gives a good understanding of the design choices and trade-offs we can have, okay? That's why we study this equation, right? Because it says that ID is proportional to V overdrive square, but in practice this might not be right. It might be some, say, I don't know, overdrive power 1 plus M or something, I don't know. But one thing is for sure, if you increase the overdrive, the current is going to increase. So that much at least you know. Second, it says that it's proportional to W by L, that is, it's inversely proportional to L and directly proportional to W. It turns out this inverse relation is not true. So again, this could be, I don't know, might be some 1 plus alpha, maybe not, I don't know. But this inverse relation as such is not true. That is, ID is not proportional to 1 by L. But again, one thing I can say for sure, if I increase L, the current will reduce. But you have the other thing, current proportional to W, and this holds quite good in practice. And that's simply because if you think about it, let's say I have a transistor, I bias it with a gate to source voltage and say some drain to source voltage. It has some length and some W. So say it carries some current, maybe I should write it here. So say maybe it carries some current ID. Now let us say I take one identical transistor, so same length and same W. I connect the gate and the drain like this. So what can you say about the current in this transistor? It should be same transistor, same gate to source voltage and drain to source voltage. ID is this. So what is the total current flowing here? 2 ID. Okay, I mean, this I can simply think of it as having one composite transistor with width as 2W, same length, the same gate to source and drain to source voltage. So here you see the current here is 2 ID, right? So this relation actually holds quite good in practice, and that's simply because increasing W is like scaling the circuit. Again, we look at circuit scaling in detail later, but again this should make sense now. And not just that, on top of this, if I apply some small signal Vi, what is the incremental current in this transistor? Some GM Vi. What is the incremental current here? So here the total incremental current is 2 GmVi. So here also it's the same, 2 GmVi, right? When I apply Vi here. So it's as though even the Gm has doubled. Again, this shouldn't be surprising, we already saw, right? If you scale the current and the width by 2x, Gm will also double. Okay, so in practice, even Gm is nicely proportional to W. So again, if that is the case, what can you say about the current density ID by W and Gm by W? They also are not dependent on width to a first order. Okay, so these are also independent of W. So bottom line is this. I mean, it's nice to have these equations, but in practice you can't rely on them to size the transistors. Okay. And what we'll do is the following. Say if you have a transistor, as a circuit designer, what are the parameters that you are interested in? Transconductance Gm, that's for sure. Say you want to know about GDS also. And you might want to know about CGS or CGG. I'll say CGS for now. Because that decides the parasitic capacitors. If you are having cascades of stages, CGS, the input capacitance is the output capacitance for the first stage, right? And also you want to know about the operating point, say the current, gate to source voltage or the overdrive voltage, drain to source voltage, and finally the physical parameters that you can control, which are length and width. And basically these are the operating point parameters, right? Okay. So now let us say you have a lookup table where for each W, each L and each of the operating point you have a tabulation of all these parameters. If you have such a lookup table, then finally let's say I find that I need a transistor with a particular GM, I can see this lookup table and find out what are the options I have, right? Straightforward, right? That's the basic principle we follow in practice. And to generate this lookup table, if you think about it, I'll have to first sweep the width. I'll also sweep length, and then I'll also have to sweep the operating point. So which means I'll sweep VGS, VDS, and to be more accurate, you'll also have to take into account the source to bulk voltage also, right? That we haven't considered here, but if you want to be really exact, you'll have to do that. So you'll have to sweep all 5 variables and note down all these guys. Okay. If you do that, you can have a huge lookup table, and then you can actually look up and find the required sizes. Okay, but let's say now here you have to sweep 5 variables, right? So can you think of some changes that we can make to this experiment so that I don't have to sweep one of these variables? So I'll rephrase the question. See here, what we are doing essentially is we are noting down all these parameters, and we are sweeping 5 variables, right? Width, length, gate to source voltage, drain to source voltage, and bulk to source. And I have to sweep all 5 because the parameters I am saving, they are dependent on all 5 variables. Okay. So is there some change I can make here so that I don't have to sweep one of the parameters here?
You can say W by L.
No. Sorry? Okay, let's say that we can ignore, but let's say to be accurate, we'll also have to include it, right? See, the problem is because the parameters that we have listed down here, they are dependent on all 5. So we have, based on what we have discussed in the beginning of the class, yeah, see, we saw some parameters that are independent of W. isn't it? So instead of saving these guys, so instead of saving GM, I'll say GM by ID. We saw it's independent of width. Or I can also do GM by W. We just saw this also independent of width, isn't it? So instead of GDS, what can I save? What did we start the discussion today? We started with the intrinsic gain, right? And if you see the intrinsic gain is proportional to GM by ID, so it's also independent of width. So instead of directly saving GDS, I can go and save GM by GDS, isn't it? Or another thing you can do is GDS by ID. Okay. And instead of the gate capacitance, what can I save? FT, right? We saw GM by CGS, that was FT. Instead of current, what can I do? No. I mean, current is proportional to width. So what is the parameter? That is ID by W, current density. Okay. And if you think about these are all not random parameters, they have some other significance, right? We just saw the significance of GM by ID, you know, significance of intrinsic gain. We saw about GM by CGS. So each of them has some significance, and the point is we choose these parameters so that they are all independent of width. So now the search space reduces. So to get these parameters, we have to sweep length, VGS, VBS. So we have only 4 things to sweep. And again, for your project, probably you don't have to worry about these 2 guys and say only think of these 2. So which means it's not be very accurate, but to a reasonable, to a good order, you can generate this lookup table. So the bottom line is this. So what you'll have to do is, and remember, you have to do it for both NMOS and PMOS. Okay. So the procedure is this: you start with an NMOS. You start from some length. Say you start with the minimum length. You sweep the operating point. So basically, you can sweep VGS. And then save all the width independent parameters like ID by W, GM by ID, GM by GDS, say GDS by ID, overdrive voltage, and GM by CGS. All of these are width independent, so I'll just save these guys. And this is basically sweeping VGS. So I'll have to repeat this for multiple values of length. Okay, so you go and repeat it for different values of length. Say I'll choose 2 times the minimum length, 3 times this length, 5 times this length, and so on. Ideally, as many different values of lengths as possible. Okay, and then you do again for PMOS also. Do the same thing again. Okay, and to sweep the operating point, can do it in multiple ways. So you can directly take the transistor. And one other thing, see, when you do this, you choose the length as something, and the width, you don't choose it to be minimum width, you choose it to be much greater than the minimum width. So say around 1 micrometer or something. Okay. So what you do, let's say you choose 1 micrometer by some minimum length into some factor. You keep changing this factor. So you can connect it like this and sweep the VGS and then save all the parameters. Or you can also do this. You can pump in a current, do a diode connection like this, and sweep the current. When you sweep the current, the gate to source voltage also changes. So again, make sure you repeat it for multiple values of length, and each time you make sure the width is around, width is 1 micron or something. Don't keep it close to the minimum width. And if you do that, I'll show some example plots. So here I am plotting GM by ID versus the current density. Again, here I have chosen only for the minimum length. If you do it for different values of length, you will get different plots like this. I don't know, just randomly drawing. So this could be for 2 times Lmin, this could be for 3 times Lmin and 5 times Lmin and so on. Again, actually this is based on one of the freely available models. So the modeling is not great, but in practice if you take a real model file, you will find the GM by ID kind of plateaus like this at lower current widths, lower current densities. But there is, this is a freely available model. So this again a plot showing the transit frequency as a function of current density. Again I am showing it only for minimum length. You will have multiple plots if you do it for different lengths also. So I'll let you ponder over why this kind of curve makes sense. You can think about it. And again, if you have advanced simulators like Spectres, you can get all these in one shot easily. But you will be using LTSpice. It's a freeware simulator, so there it is not very straightforward to get these. So to get the values of GM, GDS and gate capacitance, in LTSpice you will have to run a DC operating point, a .dc simulation. I have also explained this in the problem statement, but I will repeat it now so that it's clear. And it turns out with DC operating point you can get all these GM, GDS, gate capacitance and so on. But LTSpice doesn't let you sweep the DC operating point. It lets you run something called DC sweep, but there you can't get the values of gate capacitance and GDS. So I don't know, you can think of and do something, but to get these plots quickly, what I did was a brute force way. So what I did was the following: I took one circuit like this. Say this is 1 micron by minimum length. I took multiple copies of this guy, wherein I changed the currents in each. Okay. And then I found the DC operating point for all transistors. So that's as though I have swept the current and got the operating point. This is just a simple brute force way I could think of. You can also search and do whatever you want. And if you do that, you will get discrete points like this. I imported them in MATLAB and did an interpolation and got a smooth curve. Again, it's not very great, but it's okay. So basically what I did is this. So this is the single circuit, right? I had basically put 24 copies of this, and in each of this I changed the current. And then I take the operating point for all transistors. It's as though I swept the current for all these 24 values. Yeah, whichever works for you. So now let's quickly see how we can use these plots to do a design. I'll take a simple common source amplifier as an example. I can do a diff amp also, but that's a part of your project, so I'm not doing it. So let's say the specs are these. I want to have a DC gain greater than 10, that's 20 dB. The load cap is 1 picofarad. And I want an omega u which is 100 megahertz, 2 pi times 100 megahertz. So this is the circuit we have. M1, M2, Vi, and here I have the load capacitors here. So first I have been given what omega u is. Can you tell me the expression for omega u for this guy? What do you think it will be? Again, it's a, think about it, it's a first order system or a second order system, this guy? First order. So what is omega u for a first order system? Yeah, DC gain times first pole. What is the DC gain here? By some G out, right? And what is the pole location? G out by CL, right? So what is omega u then? GM1 by CL. So I know this is basically 2 pi times 100 megahertz. I know what CL is, 1 picofarad. So GM1, it is 2 pi times this, so that's I think 628 microsiemens. Okay. So what is the other spec that I have been given with? I have been given what DC gain is. So what is the DC gain here? GM1 by? What's the DC gain? No, not CG, DC gain, right? Yeah, the two RL GDS one, okay? Yeah, not CGS, GDS. Fine. So this should be greater than 10 for me. That's a given spec. So if this is the case, what can I say about GM1 by GDS1? Can you make any comments on this? I mean, I know GM1 by sum of the two GDS must be greater than 10. So can I make any comments on GM by GDS1? I mean, yeah, that's assuming that if both the GDS are roughly same, this should be greater than 20. Make sense? So I say choose it to be some 25, round number. So if you think about it, what I have is this. I have GM by GDS. I know the value. I also know what GM is. I need to find the current and width. So what do you think I can do? I have generated so many plots, right? I have swept operating points and captured a lot of parameters. So where should I look at to get information about ID and W? Yeah, basically I can see this guy, isn't it? If I take a plot of GM by GDS versus GM by ID, I mean, I've saved both these guys for different operating point conditions. So I'll plot one with respect to the other. I know what GM by GDS is. From this I can find what the GM by ID is. I know GM, so I can find ID. Make sense? So this is that plot where y-axis I have GM by GDS, x-axis I have shown GM by ID. So this is the DC gain, 25 roughly. So this says my GM by ID is what? 4.912 something. My GM is 628 microsiemens. From this you can find what this is, and I think this turns out to be around 128 microns. Okay. So now I know what is ID. Oops. Now I found ID. What is the other thing I have to find? Okay, and remember before this, this plot I have shown for minimum length. Okay, so the length is fixed to be minimum. So let us say I find that for minimum length I am not able to meet the required DC gain. That is, let us say your DC gain is now higher. Let's say DC gain is somewhere here. This is the gain you want to achieve. And with minimum length I am getting only so much. What can you do? To get a higher gain, what can you do? Yeah, you can do it for different lengths. Okay, if you do for multiple lengths, you will have different curves like this. I mean, that's why, I've taken only for one length, but ideally you should have multiple plots like this for different lengths. So then you can find what is the length you need to get a particular gain. In this case, conveniently I chose a value so that with minimum length I can get the required gain. So, cool. So now I found the current. What is the next thing I have to find for the transistor? I mean, I know the current, I know the length. Length is minimum length. So what is the other thing I need to find? Width I have to find, right? So again, now I know GM, GDS, ID. So which of the plots I can look to get W?
ID by
ID by W is something we stored, right? So I can do this. I can plot GM by ID versus ID by W, right? So this is that plot. GM by ID in y-axis, ID by W in x-axis. So this was the GM by ID we have, and the corresponding current density is some 83, and you can find W will be around 1.55 micron or something. Okay. So this gives what is the width to be 1.55 micrometer. So this finishes design for the NMOS. Now we'll have to size the PMOS transistor, right? So for the PMOS transistor, what all do you know? We know the ID, current, right? So ID is 128 micrograms. Anything else? We know GDS too, right? Because we kind of made an assumption initially, both GDSs are same, isn't it? So from here I can actually find GDS. So I know GM by GDS is 25. So you can calculate what GDS is. I think that will come around 25 microsiemens or something. Okay. So I have GDS to be 25 microsiemens. I just need to find the width of this guy. So what can I look at? Which of the parameters I can look? Yeah, exactly, right? This we can look at GDS by ID as a function of ID by W. You take this plot. So this is GDS by ID versus ID by W. Okay, and this is the required GDS by ID, around 0.195 something. So you know what the current density is. Again, I have chosen it for minimum length. Okay, ideally you should have multiple plots and choose a length and do it. So this is something 9.5. Current is 128 micrograms. From this you can find the width. I think that comes out around 13.5 micrometer. Okay. So this gives the width to be 13.5 micrometer. And in all of this I have chosen the length to be minimum. Okay, so one other thing, so see, in practice, in LTSpice it won't make a lot of difference, but in practice, when I have a width like this, usually we don't put a single transistor with 13.5 micron width. So what we'll have is something called fingers, which I'll explain later, but for now you can think of it as putting multiple transistors in parallel. Okay. And usually we keep the single finger width or the single transistor width to be not more than a couple of microns. So I usually might do something like this, 9 times 1.5 micron. So think of it as putting 9 transistors in parallel, each with 1.5 micrometer width. Because it turns out for there is a range of widths for which all the practical device models are good. If you use very small or very large widths, the models we get in practice might not be very accurate. But of course for LTSpice and the model files that I give you, these won't make a lot of difference. They are pretty rudimentary. But in practice, when you design with real models, this is something you should have in mind. Okay. Now design is done, but finally you should also make sure that the overdrive voltages you have are reasonable enough, right? So now the design is done, but the circuit is not yet done. So let's make the complete circuit with biasing. So this is our common source. I have the load here, CL. Now how is this drain voltage biased finally? I mean, how is the DC operating point of the drain set? How will it set? That will set the gate, right? What will set the drain? I mean, we have been looking at this, right? So in practice, how is the drain voltage of the transistor set? I mean, I can't make a diode connection here, right? See, even in your diff amp or the Miller OTA, your second stage was this, isn't it? You had a first stage here. So what was setting this DC operating point here? The overall DC negative feedback. Okay. The DC negative feedback around this guy is what will set this guy. So here also finally, if you use it in DC negative feedback, that will set this. Okay. But for now, to keep it simple, I will not do that. What I will do is, I will put a large inductor here and connect it to VCM. So what this will do, at DC the inductor is going to behave like a short. So it's as though this voltage is set to VCM properly. And if you use a very large inductor, for any frequency greater than DC, this is going to behave like an open. Isn't it? So this will behave like an open, so this will not come into picture for frequency response. So this is one simple way in which you can quickly set the operating point. But I mean, for your case, for the Miller op amp, you don't have to worry. Actually, you can put it in. Let me erase it. See, for your case, when you make the Miller OTA like this, and actually go and put it in feedback like this, connect VCM, and everything will be fine. And then you can check the DC operating point. If not, you can do this also. Okay, so that is fine. Now I'll have to generate bias voltages, that is the gate voltages. I know this guy must be biased with a current of 128 microamps. So let's say I have a current source of 128 microamps. What can I do? How will I generate the gate voltage?
We know everything, right?
Yeah, I mean, I need to generate this.
We overdrive, we can.
I can basically use a diode connected transistor like this.
What is the question?
How will I generate the gate voltage required for biasing the transistor? Is that okay? I mean, I do this. If I have the same transistor here, these two guys, if they are identical, this will generate the required gate voltage to sustain the required drain current. So now I have generated the gate voltage. On top of it, I will have to add the small signal. For simulation purpose, I will just directly do this. That's all. This is the small signal. For simulation, it's okay. Now that sets the bias for the NMOS. What about PMOS? Gate voltage of PMOS. What is the current flowing through the PMOS? Same 128. So how can I generate that required gate voltage here? Yeah, diode connection of PMOS. So you will have to do this. But I don't want to use two current sources, right? So what can I do here? Let's say I have one current source and I used it for generating the bias for the NMOS. So what can I do? I mean, you're right, here I have to have a current source. So what? NMOS, and what should I do to the gate of this guy? Make sense? So now this is like a current source. That is, this transistor is now like a current source biased with a current of 128 microamps, and this generates the required gate voltage. So I'll go ahead and connect it like this. That's all.
Can the diode-connected PMOS and the diode-connected NMOS be on the same branch?
Oh, that will not work, right? Because you are saying like this, right? So what is setting the current now?
No, with the current source.
With the current source. You think about it. I'll explain it later. This is an interesting suggestion. Think about it. We'll discuss. So there are two things. Number one, we don't have floating current source in practice. I mean, usually the current sources we have in practice, they are all grounded. See, in practice also, we don't have a current source. So what we do is, I mean, let's say I'll show for NMOS. That's what I've done. So what we do is we actually put a resistor here. That is, see, it's all substitution theorem. See, if you have a current source here, say it's 128 microamps, this is VDD, this is going to roughly sustain some gate to source voltage. So the voltage across this is VDD minus VGS, right? So substitution theorem says I can replace this by a resistor whose value is VD. So nothing will change in the circuit. So this is what we do in practice. We don't have current sources. Okay, cool. So this is how you make the circuit, and finally I did the same in LTSpice. So this is the common source, and this is the inductor connection to set the operating point for the drain, and this is the other biasing stuff. Okay, and again this dot OP runs the operating point, and this runs AC sweep. So let me show you the operating point results. So this is the operating point results.
Do you have any tutorial video how to learn LTSpice?
You can, I've attached it, you can search it online, there are lots of videos. So this is our NMOS M1. So I look at the GM of this. So it's around 643 microsiemens, and we designed for 628. It's close enough, it is not very accurate because I didn't include VDS and VBS, number one. Number two, to get the plot also I did lot of hacks, right? I got some discrete points, and in MATLAB I interpolated like this. So 2 levels of errors I have made. So I mean it makes sense that I get some error here also. And if you look at the GDS value, oops, can I erase it? Yeah, this is the GDS value. If you remember, the GDS we wanted was 25 microsiemens, and again we get close enough to that. Okay. And if I run the AC simulation, this is the characteristic I get. So the DC gain is greater than 20 dB as expected, and the other spec was omega u. So this is the 0 dB. You can see that it crossing more or less at 100 megahertz. You can see from here also. Magnitude here, can you read it? Yeah, that's 5.7 milli dB. That's basically 0 dB, right? I mean 5 into 10 power minus 3 dB, and the frequency you have is just about 100 megahertz. So this is how you actually go about and designing in practice. Okay, so you generate all these characterization plots for multiple lengths and for different VGS, and I mean then it's all plug and play, right? You in your design you find out what parameters you know. For example, here we saw first we know GM by GDS, and we wanted current and width. So you trial and errors. I mean not trial and error, just plug and play. You know this. To find the current, I can take one of the parameters which relates current, and one such parameter was GM by ID, and you can do it. It's logical, okay? And I mean, as I mentioned, finally, if you do this, you also have to make sure the overdrive voltages are all fine, right? Because here, yeah. So here I need to make sure all these gate voltages here are at a reasonable levels, because I know the drain voltage will be around say VCM. So drain is going to be at VCM. I need to make sure the gate voltage here, which is the DC gate voltage here also, is not very high so that this remains in saturation. So for that you can look at the characteristic plot ID by W versus overdrive voltage or something. You know the current density, you find what is the overdrive voltage, you can check it. Cool. And this kind of lookup table based technique is often called GM by ID based design. The initial guys who did this came up with the technique, came up with the name. So I mean if you want to search online, this is the keyword, just search for GM by ID based design. But the idea is simple. You just generate a large lookup table with relevant parameters, and then go and look at the table and get the required values. And to keep life simple, you choose the parameters to be independent of width. So that saves you one, I mean that makes sweeping the width irrelevant. So yeah, so I'll stop here.